Good morning. Hopefully I have my audio issues worked out, so please let me know in chat if audio is just a mess. Looks like there's just the two of us this morning, so we can kind of pace it to your needs. My plan is to work through Lab 8 and then work through Lab 9, and there's two parts to Lab 9. One is just a bit of code to confirm that the circuit still works. And then part 2 is introducing you to doing comparisons and using the flags register to perform some logic, some decision making in code. Let me get my my vertical camera up here. Okay, so there's no circuit for Lab 8. It's literally just the board. So we'll just attack the code. Probably we can just do the whole coding work all at once because it's pretty simple, and then we'll run the circuit using the GNU debugger, and we'll answer the questions as we go. I haven't yet plugged in my board. I don't know if you can. Oh yeah, so I haven't plugged it in yet. I'll do that after we do some coding work. Good morning, Dice K. So we're working on Lab 8. And I'll just go down through the numbered elements and do them one at a time. And I'm literally just going to do what it says for me to do. And so I'll just start with number 1 here. When you see the term immediate value in assembly, morning everybody. When you see the term immediate in assembly, that means a constant or a literal. So that's in the ARM, that's just a move instruction. Remember, the destination register goes first, so I want to move the value 0 into R0. That's the whole instruction. When to use move over when to use load takes some getting used to. So just sort of follow my lead for a while until you develop a feel for when you use move or load. But also, if you use move in the wrong place, you'll get a compiler error, and you'll learn to recognize the compiler error as telling you, oh, I should have used load instead. I have a little bit of network lag. I hope that's not affecting you guys too much. But you can just let me know in chat if you notice any problems. Okay, so that's all that is. The other thing about immediate values is that you can put a pound sign in front of them, but for our assembler, that's optional. So occasionally you'll see me put the pound sign, and occasionally not, but it's optional, so you can do whatever you want in terms of the pound sign for immediate values. So immediate just means a literal. Okay, so number 2 is to do the code to add 1 to R0, so that's an add instruction. We also have the option of using the add S instruction, but since it doesn't say anything about that, I'm not going to worry about it. So I'm just going to add the destination where the result goes is R0, and then I'm going to add R0 and 1. And again, since 1 is a literal, you can proceed it with the pound sign, but you don't have to. Remember also, by the way, that these are decimal, and you can tell that because there's no symbols in front of them. In ARM assembly, if your source and destination are the same place, you can eliminate one of them. So, hello, good morning. So I can do this, and this is the same thing as saying R0 plus equals 1 in ARM assembly. I found that most people in the end probably prefer this shortened form of the instruction. But if it makes you uncomfortable, you can say R0 equals R0 plus 1. Or you can write R0 plus equals 1, either way. So that's number 2. Notice, by the way, so the number 3 code will be on the line below it. All right, so another move. This time the destination is R1. I can make this bigger. Let me make this slightly bigger for you. Okay, so I'm right here in the main loop. I'm on number 3. So I'm going to move the immediate value 2 to R1. Because that's what the instruction tells me to do. Then it says to add. So R0 equals R0 plus R1. And again, if the destination and source are the same here, I can eliminate and just say R0 plus equals R1, which is I find how most people like to write it. I'm saving after each of those lines just out of habit. Then another move. So this time I'm moving into the destination R2 the value 3, which again I can put a pound sign in front of it, but I don't have to with our assembler. Okay, so now I'm going to do I'm adding again, so R0 equals R1 plus R2. This time I cannot eliminate one of the arguments because they're not the same, you see. So R0 equals R1 plus R2. It has to be written that way. There's no other way to do it. Maybe for this one time, I'll go ahead and no, I don't want to do that. Let's just wait. So number 7 is to go inspect a register and see what the value is in it. Now what I would expect it to be at this point, let's see, R0, what would I expect R0 to be at this point? So R0 is 1, so R1 is 2. So at this point I'm saying R0, which is 1 plus 2, should be 3 at this point. And then I'm adding, that's a lot to keep straight, isn't it, without writing it down. R0 is 3 at this point, let's see, but R1 never changed. So this is really just 2 plus 3 is 5. So what I would expect is 5. I'm going to put a question mark next to that so that when we run it, we can confirm that that's true. In hex, that would be 5. But I'm going to put a couple question marks there because we'll inspect the register at runtime and see if what we're guessing is correct. We don't really have to do this guessing part, but I just did that to sort of get our minds warmed up. At least my mind needs to be warmed up. Okay, so that's that whole sequence. I just did what it told me to do, and then when we run it on the board, we can inspect the register right after this instruction executes, and we can see what R0 has in it, which we anticipate is going to be 5, which is R1 was 2, R2 is 3, so 2 plus 3 should be 5. Okay. Part 2. So using subtract instructions. So here we go again. So we're going to move into the destination R3, the immediate value 9. You can write that in hex if you want to, but decimal is easy to understand here, so I'm going to do that. Now we're going to do a sub. So sub, the result goes in R3, and I'm going to say R3 minus 1. Since these two, the source and destination are the same, I can eliminate and just say R3 minus equals 1, like I would in C++. number 3. So move the immediate value 4 into R4. My guess is I meant to put a minus here. Why would I put a plus? Well, I'm going to do it because that's what I wrote. So R3 and R4. Well, let's just do it, since that's what it's telling me to do. R3 equals R3 plus R4. Good morning. We're getting some more people in. Good morning, everybody. Since these are the same, I can just say R3 plus equals 4, plus equals R4. Move into R5 the immediate value 2. I'm doing these as decimals. Morning, Brooks. So I tend to use decimal when that's easier and easier to read, and I use hex when I'm doing like the bit manipulations because I find hex is easier in those situations. But just sort of basic math and counters and stuff, I often will just use decimal. It's totally up to you what you want to do. Okay, so there's move immediate value 2, which again, I could have put a pound in front of it, but R assembler doesn't require it, so I didn't. Now I'm going to do another sub. So sub R3 equals R4 minus R5. And of course, you don't write the minus, you just put the arguments in place. Since these aren't the same, I can't reduce the number of arguments, so I just have to say R3 equals R4 minus R5. I'm going to do the same thing as I did before, which is to try to work it out in my head what R3 should be. Let's see, R4 is 4, R5 is 2, so R3 should just be 2, which in hex is 0x2, but I'll put a question mark there because I will confirm that when I run the program on the board, and I will check the register contents for R3. Okay, so notice in each part it's telling me what instruction it's anticipating. So when we use add s, what we're doing is we're asking the processor to set status flags for us. So the processor will run the add, and then it will set flags in the program status register to communicate to us about what happened. And I'll explain that as we write the code. Okay, so I asked this one a bit tricky here, because it turns out if we do move into R0, this very large value, 1, 2, 3, 4, 5, 6, 7, 8, that's 32 bits worth. That's bigger than you're allowed to do a move with. So moves will do at most 4 of these. And if it's anything more than 4 nibbles, which this one is, 2, 3, 4, then you use a load and you use this pseudo instruction. You may remember, you may not, but I asked you a question on a homework about this pseudo instruction. So by pseudo instruction, we just mean we're using a little assembler trick. The assembler is actually going to do some work for us at the time that we compile it. But if this value that I'm trying to put into a register is more than 4 nibbles, this one's 8 nibbles, then I need to use the load instruction with the equal symbol to get that to work. I'll remind you of that as we work through labs, and I'll point out to you when I'm doing that. I probably should have been nicer and said load that immediate value. But you need to use a load for a more than 4 nibble value, which that is. Okay, so this section, part 3, is add s. So I'm going to do an add s here. So R0 equals R0 plus 1. Since these two arguments are the same in ARM, I can just say R0 plus equals 1. Add s means that the processor is going to set status flags. So on number 3, that's really a question that we can't write code for. We just need to check the program status register when we run the program to see the bits that are set. And I'm going to go back and I'll show you the status register bits when we run the program. And then we'll look to see. But hopefully everyone recognizes that this is all the bits set. And if you add one with all the bits already set, it no longer fits in the target register. So what we'd expect to see is a carry and or overflow after this add. So the processor should recognize, oh, that result doesn't actually fit there. So we're either going to see the carry flag set because the processor says it doesn't fit, or we're going to see the overflow set, bit set. But we'll find that out when we run the program. One of those bits is going to be set, which is the processor telling us that thing that you just did didn't fit. And then what will R0 be at that point? Well, we'll have to just find out. Does anyone have a guess, by the way? Well, if you take all ones, yes. So Vince is right. What we'd expect is 0. So if you do the binary math where you add 1 to all these ones, it's going to be 0, carry, 0, carry, 0, carry, 0, carry, 0, carry, until you get all zeros, 32 zeros, and then you're going to have a carry bit because it had nowhere to go. It wouldn't fit. So that's good. And let's put that as we think that might be what happens, and we will confirm that when we run the circuit. Okay, and then part 4, using subtract setting the bits. So I'm going to move the immediate value 0 into R3. 0 doesn't require the load R trick because it's just 0. Then I'm going to do a subs this time because I'm in the subs section. So subtract and set status bits. So R3 equals R3 minus 1. Since these first two are the same, I can just say R3 minus equals 1. Sorry about that. Yeah, I can see that now on my Twitch screen. There's a lag. Internet's getting exercised. All right, so hopefully, so where I'm at is I'm on part 4. I can see the lag on the screen. I'm on part 4, which is using subtract and set status bits. My screen is completely frozen, by the way. I'm refreshing. All right, maybe that worked. If you put anything in chat in the last 5 or 10 seconds, I just refreshed, so there's still some lag going on, but I may not have seen what you put in chat, so please add it to chat. Everything that you really, really, really need is going to happen on the screen, so don't get too worried about the audio. So I'm on part 4, and I'm still lagging, by the way. I don't know if you guys are, but I'm lagging pretty bad. So I'm on part 4 using sub S. So I did step 1, which is move 0 into R3. Yeah. We're just going to have to fight the lag a little bit. I'll try to not go too slow, but slow enough where everything you need appears on the screen in front of you, at least at some point. Okay, so I did step 1. I did step 2. I used sub S this time because we're in the section that is communicated. I can see on my screen that there's lag. So sorry about that. I wish there was anything we could do about it short term, but we'll just deal. It could be my internet. I'm not sure. Okay, so maybe you'll hear me. Like I'm completely frozen. Okay, we've written all the code though at this point, so hopefully the internet will just catch up and start behaving. One thing direct, so numbers 3 and 4 here are things we'll confirm when we run the program. But this time, what we'd expect if we subtract 1 from 0 is that we're going to get -1. So we might expect the negative status bit, because if we do a sub S and the result is negative, then the processor will set a status flag telling us that, hey, that your result is negative. So we're going to guess that the negative bit will be set, possibly others, but the negative bit we think will be set. So the value in R3, -1, looks like this. That's a 1, invert all the bits and add 1, so that 2, 3, 4, 5, 6, 7, 8. We think that R3 may look like this because that's what -1 and 2's complement looks like, but we'll run the circuit and we'll find out. My connection is cleaned up a little bit. I hope that's true for all you guys as well. And if you asked me a question and I missed it, I apologize. I refreshed a couple of times because I was lagging super hard as well. I am sort of, as I watch the Twitch screen for chat, I can obviously see the lag that you're experiencing. So for me, that's kind of cleaned itself up right now. Hopefully that's true for you. Okay, so now it's time to go compile and run this thing. So I'm gonna plug it in. Plugging it in now. And you'll see the lights will come on here for you in a sec. So I have no circuit attached because Lab 8 doesn't use the breadboard. It's just this board to experiment a little bit with add and subtract instructions. Okay, so now what I want to do is go through the recipe and compile and then do the GDB thing. Yeah, it's still lagging for me, by the way. I keep getting little indicators that it must be lagging. Apologies. I guess well, what you could do on your end is go to like lower latency or something. Anyway, let's go through the recipe. So I'm just showing you my browser screen so you can see what I'm doing here in terms of going through the recipe. So I'm going to go grab, load up the Lab 8 page, and then I'm going to run through the the steps. So I'm going to compile the code I just wrote. And when nothing happens, that's a good thing. I'm going to produce the executable, the elf file. I'm going to start up the OpenOCD channel. I'm going to do this in a separate window like we always do. Let me show you that real quick. So I'm going to have two terminals here. One of them I'm going to run OpenOCD in. If I can get that to show for you. Oh yeah, hold on, let me change this. Nope. Nope. I'm trying to show you my terminal. Okay, so there it is. All right, so I have OpenOCD running in the background there, and then I'll do the remaining steps in the other terminal. So fire up GDB. Okay, just making sure you can see stuff. Still have OpenOCD because I need that running so I can do the debugger steps. File main.elf. So I'm going through the GDB menu, recipe rather. Target remote, localhost. Load. Monitor reset. Halt. I'm afraid you might still be getting lag. Which is frustrating. But hopefully you're seeing the activity on the screen. So my challenge now is to simply step through the program and answer these questions. So I'm going to step through the code until right after I've executed this sub, and then I'm going to inspect R3 and see what the value is. So here we go. And what I'm doing, if you don't remember, but in GDB, it's going to tell you what's about to happen. So it's hard to get used to, but what you're seeing every time you step is the next thing that will happen the next time you step. So this move right here has not happened yet. It's the next thing that will happen when I step. And what I'm looking for, I'm just going to keep stepping. I'm in the wrong section, by the way. So this move 2 into R1, that's right here in my code. You'll notice, by the way, GDB actually knows the line number. So I'm on line 42 of my code. So that has not happened yet. It's the next thing that will happen. So add R0 equals R0 plus R1. That's the next thing that happens. So I'm going to step that. Now the next thing that will happen is move 3 to R2. Now the next thing that happens is R0 equals R1 plus R2. All right, so that just executed. So now I want to see what R0 has in it. So I'm going to inspect or info register R0. And it does have the 5 like I anticipated. So the answer that I leave in that comment there is 5 in decimal, or 0x5, the hexadecimal. So that's part 1 complete. I ran all those instructions and then I confirmed the answer to number 7 and I wrote that in my notes. And that's what you will do for your lab, is write down your answer to fill in the blank and leave that there. Is how I confirm that you got the lab right. Okay, part 2. So you'll notice the next instruction is line 56. So that one hasn't happened yet because I haven't stepped past it. Move 9 to R3. So that's line 56 in my code right here. So I'm going to step that. There's the sub. R3 equals R3 minus 1. Step that. Move 4 into R4. Step that. R3 equals R3 plus R4, or R3 plus equals R4. I'll step that. There's the move 2 into R5. I'll step that. This is the one that right after I run this, I want to check. So I'm going to go ahead and step to execute that. And then I'm going to inspect or info register R3 to see if it is what I thought it was going to be. It's 2. That's what I thought it was going to be, was 2. So I can take the question marks off because that was in fact correct. This one's taken longer than I thought it might, but hopefully you're sort of seeing how this works. We may only get through part 1 of lab 9 and we'll just sort of keep trying to catch up as we can. Okay, so part 3. There's only 2 instructions and then I'm checking status registers. Hold on, I'm doing something super secret in the background here. Okay, part 3. So I need to, this was the last instruction that I haven't caused to execute, so I'm going to step and execute it. Then I'm going to step R01. I don't know what that is. Interesting, it doesn't show the add S, but that should be what's about to happen. I don't know why the add S doesn't show, but so be it. I need to execute it. My GDB is misbehaving. I don't know if you can tell, but that R30 line 84 should be a move 0. So something's funny going on with GDB. I'm not going to worry about it. What I do want to do is do an info registers, and I'm going to do an info on all of them first. The one that I'm interested in is this one right here, the program status register. So I'm noting that there's a bunch of zeros, and then this top nibble is a 6 right here. That top nibble is a 6. So let me show you why that top nibble matters. So on the status register page, what we talked about on Tuesday, remember, it's this top section right here. That's the top 4 bits, 31, 30, 29, 28. That's the negative, 0, carry, and overflow bits. So what I'm seeing with that 6 there is that these bits are in the pattern 6. So I'm going to write that down in code. The pattern is no, let's see, 2 to the 0, 2 to the first. So no 2 to the 0. There is a 2 and there is a 4 there. So that's the bit pattern that I'm seeing for those top 4, which means that, do I have those right? It's 1, 2, 4, right? Aren't I seeing a 6? What do we, oh, carry and or overflow, but we're not seeing either of those things, which is funny. Unless something happened and that's why the add S didn't show. Let's see what is in R0 while we're at it. R0 is 0. That's what we anticipated, so that was correct. The program status register is 6, and maybe I wrote these wrong. See, 2 to the 0, 2 to the first, 2 squared. It should be those 2 bits. Oh, we did expect that, didn't we? So 0 is in fact what we got as a result, and we got a carry. So not overflow, just carry. Okay, so I feel better because that is in fact what we were expecting to see. I'm in the wrong place for that, by the way. That was up here. I don't care about any of the rest of those, but I do know that the top nibble is 0, 1, 1, 0. And if you look at the bit allocation, that means that it's not negative, but it is 0, that bit set. It is carry, and it's not overflow. So that's the result there. And so my answer for 3 will be the carry bit was set, I saw. The answer for 4 is that R0 has 0 in it. But I also had a status bit that told me that, as it turns out. Okay, part 4. So way back, this is the next instruction for me. It doesn't show the move because something funny is going on with GDB, but I know that's the next thing. And then this is the sub S on line 86 is just showing the wrong line number too, but that's fine. That's the sub S, so I'm going to go ahead and step that to execute it. And then I've got a loop thing going on, but that doesn't really matter. What I want to see right now is what's the program status register bit look like. So let's do info registers. So XPSR, so notice the high nibble is 8 now. So XPSR is 0x8, 1, 2, 3, 4, 5, 6, 7. That means that the high bit is this. And what that means is that the negative bit is set. So it is as we expected. You can't see that part. You cannot see. So I'll go back. I'm right here. For me, line 90, PSR. That was an 8, so the top nibble is 1, 0, 0, 0. And what that means is that the negative bit is set because that bit, that 2 to the 31st bit, that means negative. The value in R3, I can confirm, is all F's, which in decimal looks like -1, so that answer is also correct. I'm going to highlight what I did on the earlier one because I forgot to hide my browser for you to see it. So for part 3, when I got down to checking the status register bits, I noticed that the top nibble had a 6 in it, which is 0110, and that tells me that the 0 bit and the carry bit, so we could say that if we want to, 0 and carry were set. And the value in R0 was 0, which is what we expected. And then in part 4, which I finally unhid Brave so you could see it, part 4, after we ran these instructions, we saw that the status register had 0x8, something. It's only the first nibble we care about. So 8 in binary is 1, 0, 0, 0, and that tells us that the negative bit was set as we expected. And then we confirmed that the value in R3 was all Fs. All Fs in 2's complement is -1. That's lab 8. Okay, so does anyone have any questions for me about lab 8? And you can go back and review. And hopefully you have all the working code, so if you need to, go back and what I recommend you do, just to feel more confident about it, is to actually run it for yourself. Use GDB to inspect registers, step the program, inspect registers, and confirm by your own observation that these answers are correct. So I'm going to just let us gather our breath here for 30 seconds or so, and I'll wait for your questions before I load up lab 9 and work on that. Okay, so you're about to see my, sorry, my lip itches. You're about to see my editor close, and then I'm going to reopen it on lab 9. So I'm also going to close down OpenOCD for now and unplug my board because I'm about to wire it up to my external circuit. So I'm going to close this down. I'm going to go to GDB and I'm going to quit that. I'm going to go to OpenOCD and I'm going to Control-C to quit that. Although I'm going to leave that extra terminal open because I'm about to reuse it again. Interesting that you're still seeing stuff, whatever that means. What else do I need to do? Oh, I'm going to unplug my board. Maybe. I'm going to unplug my board. For some reason that's gone cold. Yeah, I need to kill my camera real quick and restart my camera on my board, so give me a sec to do that. Oh, it's because I just unplugged the camera and not the board because I'm dumb. Yay! Okay, so this time I'm going to unplug the board. So unplugging the board because I'm about to wire it up to an external circuit. I'm also going to switch over to the other lab. Okay, so lab 9. Sorry, I don't know what's going on half the time. I do have a microphone coming that I'll pin to my shirt. But I was fiddling around for a second with all my equipment to try to get it back in. So hopefully that fixes itself. If not, everything that you need should appear on the screen in front of you. So I have the board disconnected for now. It uses the same circuit. I can't find my wire that I want. It uses the same circuit from last week. So lab 9 is this same setup, I believe. Let's confirm that real quick. It has a fifth light on it, so we'll have to address that. D8 PA. All right, so it has a fifth light on it. So let's wire that up and at least get part 1 done today. So we need to add a fifth light to this. So I'm going to get myself an LED. The colors do not matter. I need a 220 ohm resistor. I need a ground wire for it, and I need a lead to connect to the board. So I'm going to add myself a fifth LED, and I'm just going to add it up here at the top. If I can find that stuff. Hold on, I'm missing those pieces, so I do have an LED. You can see that. I do have an LED, but I got to get the other pieces real quick, so hang on. Okay, so pay attention to the resistors, please. I don't know if you can see it. 220 ohm resistor for the new LED, just like we've been doing on all the other LEDs and as is shown in the diagram. So I'm using the diagram. There's a fifth LED now. So I'm just going to add that. I'm remembering, by the way, my long legs are always to one side. So I'm going to bend this LED at the knee and then kind of use my same pattern I've been using to wire it up. The colors don't matter. Use whatever color you want. I'm going to use a 220 ohm resistor to bridge the channel on the same row as the long leg. This one's fighting me, as they always do. Think I got it? All right, that one was a battle, and I don't think I've won yet even. All right, there, I think I've got it. That one was a pain. Hold on, I dropped stuff everywhere. Okay, so now I need a short wire and a long wire. I just put a wire in my T, by the way. Short wire and a long wire. So the short wire, I'm gonna go from the short leg next to the LED. So just like we did last week, short leg of the LED to ground on the board, because I can just ground them all off of one connection and move that over a little bit. And then a longer wire from where the resistor goes and out, because that's going to eventually connect to the board, and out to connect to the board. Okay, so I think we do just have enough time to write the code to test this circuit. So you won't do we won't finish lab 9 this week, just lab 8 finish. And then lab 9, since it's in 2 parts, we'll finish that. So you'll just send me, if in doubt, send me the work that you've done, but if you're confident about what I'm saying, I'll put it in chat. No, I won't put it in chat. I'll make a note of it in the video notes. You can hold off on the lab 9 stuff until next week, but we are going to do part 1, and part 1 is just to make sure the lights work. Okay, so wiring this thing up, noting by the diagram here that I'm going to take this new LED that I just did and connect it to D13. And I know you can't really see that, but that first one, that LED right there, I wired, so that's long leg to resistor, resistor over the channel, long wire to D13. On that new LED, so short leg to wire to ground, just like we did the other ones last week. So this second one, using the diagram, it tells me to take it to D12. The third one, I'm doing them in the order that the diagram shows. The third one goes to D11. The fourth one goes to D7. And then the fifth one goes to D8. And then I'll connect the ground wire to ground on the board. I'm going to use this one right here. Right next to D13 is a ground. Okay, so that's everybody wired up. Hopefully the audio, I've been playing with the game, but I will have a better mic possibly by tomorrow. I don't know if you've tried to order anything from Amazon lately, but you can't get anything from Amazon because they're prioritizing paper towels and toilet paper that they have none of, so go figure. Okay, so part 1. Assuming we're all wired up. If you took your circuit apart from last week, then bummer. I just used the diagram. So not really much I can do to help, just a whole lot there. Hopefully you're accustomed to wiring it enough that it just does what you want it to do. All right, so let's do a little bit of code. I am working with main1.s in lab 9. So part 1 is just enough code to confirm that the circuit works. So what I'm looking for is the numbered items. And thankfully, there's only 3 of them. Is that true? Yes, it's only 3 of them. I know because I created it that the purpose of this main one is to make sure that the lights actually work. Okay, so pin settings. So if you remember, if you don't, then you're about to be reminded. The mode register is how you set these pins to be outputs or inputs or other things. So for outputs, which is what we want these all to be outputs so we can send electricity out on them and turn on the lights, the pattern is 0, 1. So the mode register has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 28, 29, 30, 31, 32. Has 32 bits. I'm worried about A5, A6, A7, A8, and A9. So I don't care about A0. I don't care about A1. I don't care about A2. They're 2 bits per for mode. I don't care about A3. I don't care about A4. But I do care about A5. And I need A5 to be 0, 1. So those 2 bits right there are A5. So this is A0, A1, A2, A3, A4, A5. I need that one to be output, and 0, 1 is how you make it be output. I need A6 to be output. I need A7 to be output. I need A8 to be output. And I need A9 to be output. Going to the left, I can just ignore the ones I don't care about. So in hex, that looks like, let's see, 0, 1, 0, 1 in hex is 5. Correct me if I make a mistake, please. So this is 5 in hex. This is 5 in hex. This is 4 in hex. And then 2 zeros. So that hex value captures the bit pattern that I need to make all those be outputs. And then it says use LDR. And the reason why it says to use LDR is because the bit pattern is more than 4 nibbles. So load that into R4. Okay, so loading into R4. I'm using this pseudo instruction. Why R4? Because it told me R4. So I just did what it told me to do. And be careful. Some people want to write more stuff. And you'll get used to when you should. But in this case, that's it. Don't write anything else. That's the whole thing. That's the first code. All right. Piece number 2. Use the value in R4 to set the bits in R2. Well, setting bits is the OR instruction, and I want to set into R2. So what I want to, using the pattern that I set up into R4. So I'm going to OR R2 against R4, which is that pattern that I just computed. And then if I go down here, a toggle, so that's EOR. But I need to compute for the output register. The mode register is 2 bits per, so I computed that. The output register is 1 bit per, so I have to remind myself of that. So the output register is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's only 1 bit per, so I only do 16. And 1 bit per. So this first bit right here is A0. I don't care about A0, so I'm just going to zero it out. I don't care about A1. I don't care about A2. I don't care about A3. I don't care about A4. I do care about A5. I'm targeting that one. I do care about A6. I do care about A7. I do care about A8. A9. I need to finish the nibble, but I don't care about A10 and A11. And then I can just ignore the rest because the assembler will handle that for me. So toggling is EOR. This one does require that you inspect the code. So the register that has my data in it right now is R2, if I look at the instructions above. So I got the address of the output register. I dereferenced the address to get the current value. Now I'm going to manipulate the value by EORing it with my new pattern, which is 0x. This nibble is 3. This nibble is 14, which is E. And then this nibble is 0. So my pattern is 0x, 3E, 0. We're coming down to the last couple minutes, so hopefully you'll bear me out for this last step. There's only those 3 things for part 1 of the lab. In theory, what we want to have happen when we compile and run this code on the board is that all the lights just flash on and off. Let me, I'm not showing it to you. Hopefully you don't need to see it, but I'm just going to go through the same old steps that we always do. And then I'll show you where I'm being careful. And you're not seeing my terminal, I think, are you? No. Okay. So let's be careful right here. Because we're working on a program on a source file called main1.s. So the recipe just says main.s. So let's be careful that we're actually referring to main1.s here. That's the file that has the code we just worked on. We can leave the rest of this line alone. Just make sure that the compile command is actually touching on your main1.s. And once I have that part, then the rest of the recipe can just be done through. So there's the compile step. I'll do the create the executable step. I'm gonna open OCD in the other terminal screen, or at least that's what I want to do. And hopefully you will see that when I do it here in a second. I didn't plug in my board. So I'm plugging in my board. So I unplugged the wrong thing because I'm dumb. Now I didn't plug in the thing because I'm dumb. All right, try the open OCD step again. All right, that's better. So you should see in the terminal behind there that OpenOCD is now running. Now I'm going to go do the GDB steps. If I can get the terminal that I want. All right, so now we'll do the GDB steps. In the other window, load up the ELF file, target remote localhost :12343, load the code onto the board. Reboot and stop. So I'm not going to step this time. I'm going to do a continue. I'm just going to let the thing run. What I want to see over here is that all these lights flash on and off. If they do, then everything's perfect. If they don't, then I've got a problem that I have to go fix. All right, so here we go with continue. So I'm down right here. I'm just going to do C for continue. And they're all flashing on and off. So that's part one. That's just a test to see that the circuit is correct. That's not really the lab. That's just using the software to confirm that the circuit is actually correct. And they're all flashing off and on. That's exactly what I wanted. Okay, so I've gone on plenty long enough. I'm seeing a little bit of lag. So hopefully, there it goes. Okay. So when I'm broadcasting, the Twitch screen is like 5 seconds behind me. So this is actually how this is designed to work in class, by the way, because you're going to do some homework that I think should help you understand better what the second part of Lab 9 does, which is what we are going to sort of combine those two things probably next Tuesday. So next Tuesday we'll finish Lab 9, and then we'll also talk about, we'll use the homework questions to sort of help us through that, and then we'll move on to Lab 10 a week from today. So I'm going to shut up here and wait for a couple of minutes and see if you have questions I can answer for you. I'm going to put some notes here. So Sunday is the 3rd, 4th, 5th, April 5th. Saving this for myself. Lecture notes, April 2nd. Okay, so that's all you're responsible for submitting this week is the code for Lab 8. Oh. And whatever homework we were working on this week, which was 8. Homework 8. Okay, that's my whole show. And again, I will sit here for about 5 minutes, and I'm happy to sit here longer if there's questions, but I'll wait for a few minutes so that if you encounter a problem right now, you can deal with it. You can always email me, of course. You too, Vince. Thanks. Appreciate it. Hopefully the audio was not so terrible it was unusable. Everybody have a good day. Some of you I'm going to see again in a little bit, so sorry to you that you have to see me on screen like this so much. You too. Have a good weekend, everybody. Thank you. Yeah, I can move it for you. So let me hide that one. Oh no, I hid the wrong one. Hold on. Hid the wrong one. Hold on, it does a funny thing. So let me get... where did it go? Where did it go? Not... oh, this. Okay, here's the... do you mean the part where I did continue? Which part of the recipe? I can go back through the recipe if you want. So let me kill... so I'm going to Control C to kill this, and I'll go back through the recipe real quick. So the recipe for this lab, we start with the compile, and that's the one to be careful about. Again, though, stupid OBS. Okay, so hopefully you're seeing this thing. The first step of the recipe you got to be careful about, Daisuke. So the first step, the recipe says main.s, but the file we were working on was named main1.s. So make sure that you change that, because we were just working on a file called main1.s. So we have to update this step, the first command of the recipe, to refer to the file that we're actually working on. And then the rest of the recipe is the same as normal. So then we produce the ELF file. Then we launch OpenOCD. But we do that in the other terminal. So make sure make sure, I'm just going to hide it over here, but OpenOCD goes in another terminal. And then we do the GDB steps. So just keep doing that. the GDB step. So now we load up the ELF file like the recipe says. We connect to the board. Load the code. Reboot the board. And then continue. Now I often will just type C for the continue part, but continue just means run. Don't wait for me to step, just run. At which point the board starts going off. Darn it. Yeah, it doesn't handle this very well, my software. I keep swapping this out for the other one. No, so the GDB step does not need to change. It's just that first, literally just that first compile command, and everything else stays the same. I'll put it in the notes, by the way. So notice the only thing that changes is literally that spot right there. Nothing else has to change. So I'm not in a rush, but if everyone has their questions answered, type continue. Anyway, so if you're still working, you can just sort of give me a heads up to wait on you while you get to a question, or if you need some time to think, just let me know, and I won't stop the stream until I'm sure to have answered your questions. All right, nice. So that's part one. So look at that page of notes up there, what's due. You're welcome. What's due is homework 8 and lab 8, and then we'll work on part 2 of lab 9 next week. We just wanted to get this part started so that next week goes a little faster. So please don't pull your circuits apart so that we can just use this circuit where we left off. Okay, so I will see everybody on Tuesday next week, hopefully. Hopefully you'll have a good weekend. Email me if you have questions that didn't get resolved, and I'll answer it by email. Otherwise, take care.